So in the last video, I introduced you to the idea of magnetic fields by using the example of an actual magnet. And the reason why a magnetic field is generated around a magnet has something to do with the electrons. So magnetism is actually generated by electricity. So electricity and magnetism are connected with one another. So now I'm going to talk about an example of how a wire generates a magnetic field. So let's say I have a conducting wire and there is a current traveling through that wire. Let's say it's going in this direction. Because the electrons are moving, they actually generate a magnetic field. So in order to determine where the magnetic field is, or to draw the magnetic field lines that are occurring as a result of this conducting wire, we have to use something called the right-hand rule. Now there are two right-hand rules, but this is the first right-hand rule. So the first right-hand rule. And for this right-hand rule, your thumb is always going to point in the direction of the current. So the thumb points towards the direction of the current. And then your fingers curl around the wire and point in the direction of the magnetic fields. Now this is going to be, I'm going to try and demonstrate this as best as possible underneath the Elmo, but it's a little bit difficult to tell just because I'm sort of limited by my camera here, but let's just do the best that we can. So again, I'm just going to show my hand here. So you can see that what's going to actually end up happening is my thumb is pointing in the direction of the current. And let me actually try and maybe use the marker here to help out a little bit. So my thumb points in the direction of the current, and my fingers are actually going to curl around the pen like this, right? So they're going to curl around the current carrying wire, and wherever they are in a certain position will actually show the direction of the magnetic field. So if this is the wire here, if I point up over here on the right hand side, my fingers are curling and they're actually pointing down into the page, right? So if I wanted to show the electric field, the magnetic field over here, it would be into the page, which I could indicate by putting a bunch of X's. Okay. Now, oppositely, if I were to go to the other side, again, my thumb still points in the direction of the current, and now my fingers are going to point in the direction of the magnetic field. And here you can see my fingers are actually pointing up over here on this side. So that would be out of the page, which I represent by dots. Now, if I wanted to look, say, in front of the wire, so like up here, if I were to hold my hands like this, now my fingers would be pointing in this direction to the right. If I wanted to go down behind the wire, then they'd be pointing, as you can see, in this direction, which would be to the left. So we've got to think about it three-dimensionally. So a magnetic field is actually generated around this wire. So you can imagine this cone, and I'll try, and I'm horrible at drawing anything three-dimensional, but like this cone around the outside would actually show the magnetic field. Okay, and again, this is the best that we can do given the limitations of trying to do this underneath the document camera. Okay. Now, if we look at the magnetic field, let's say I was here at this position 1, or I was here at this position 2. There's going to be a different magnetic field at each one of these positions. And it's based on two different factors. And this should be pretty intuitive. So let's say that you are close here and you're further away. Just like with any other magnetic field or magnet, the closer you are, the more force you are experiencing, right? So actually the strength of the magnetic field is stronger the closer you are to the current. Now, also, if I were to increase the current or decrease the current, that is going to affect the strength of the magnetic field. So I'm going to give you the equation now. We'll look at what that means. So the equation for calculating the magnetic field around a wire carrying a current, which we learned in the last video was B for Teslas, is equal to, now there's a weird sort of constant that comes before it. It's called mu sub naught, which is it's called like vacuum permittivity, which is, or excuse me, vacuum permeability, which is different from vacuum permittivity, but it's all about how easily an electric or a magnetic field is going to, penetrate through space. And in this case, we say over 2 pi, and that takes into consideration this circular orientation of the magnetic field. And then what's really important is here that we have I, the current on top. So the bigger the current, the bigger the magnetic field, over R, which would be the distance you are from the wire, right? So if you have a big distance, that makes the magnetic field smaller. If you have a small distance, it makes the magnetic field bigger. And then likewise, if you have a large current, large magnetic field, and then a small current, a small magnetic field. So this both shows you how to figure out the direction, but also the magnitude of a magnetic field that arises around a current carrying wire.